Students, I hope you are all well and healthy and ready to learn a new things. So my name is Palak Patel. I am working in the Mahatma Gandhi Institute of Technical Education and Research Center, Navsari in Civil Engineering Department. I am going to teach you the subject is design of reinforced concrete structures. In this subject, we are going to learn design of flat slab. In the previous lecture, we discussed introduction and learn without drop and column head flat slab design. So in this lecture, we are going to learn with drop and column head flat slab design. So first of all, we have to understand types of flat slab which we discussed earlier, like without drop and without column head, without drop and with column head, and with drop and with column head. I hope you understand this. So in the previous lecture, we learned this without drop and without column head. So this type of design we learned in the previous lecture, or in this lecture we are going to learn with a drop and with column head design, right? Flat slab design. Okay, so first of example with drop and with column head. So we are going to learn this in the word file, right? So here is an example, a design an interior panel of a flat slab having equal panel 6 by 6 meter. Look at here, the dimension is fixed, panel dimension is fixed, it's 6 by 6 meter. The internal column are 500 mm, column dimension 500 mm in diameter means here is a circular, column is a circular, so column head is 100 mm in diameter. So if column is circular, that's why column head is circular, right? The story height above and below slab is 4 meter. This is the story height, means a column height is given. If story height 4 meter means column height is 4 meter. Okay. Design a flat slab with a drop and column head. Okay. Take live load 4 km square, M20 concrete, Fe 415 grade of steel. Okay. And this example is asked in May 2017, November 2018. Okay, so we start the solution, right? First step is depth of slab. We have to find out depth of slab from where? IS 456 2000, page number 37, 38. On this page number we can find out this equation, L by D 26 into MF. I explain everything in the details in the previous lecture, as well as so many lectures I will explain this thing. Why this is 26? Because it's a continuous slab. How to find the modification factor from the chart? By the assumed PT 4% and MF 1.3. So we are going for the flat slab. L is equal to longer span, but here is a no longer span, all the span are same. Okay, longer dimension is same as well as shorter dimension. We have a longer dimension is 6 by 6 meter, right? So longer and smaller both are same, so there is no longer dimension. But from the IS 456 clause number 31.2, page number 53, we have to solve this equation, and then after we found the depth 177.51. So we provide minimum depth is 125 mm is required. So we provide overall depth capital D is equal to 200 mm. Right? These are the effective depth. 200 minus 5 by 2 minus clear cover. So 200 minus 10 by 2, because we assume diameter is 10 mm. So D is equal to 175 mm. Right? Now we have one more thing. This is the depth of slab is fixed. Okay, we found that depth of slab. Now we are going to find the drop dimension. So generally thickness of drop is kept 25 or 50% more than the thickness of slab, right? 25 to 50% more than the thickness of slab. So provide the drop is 250 mm. Provided the depth of drop is 250 mm, right? So small d for the dwarf portion is 250, 10 by 2 minus 20, so 225 mm. Okay, this will explain the figure. Just give me. Now we discussed earlier that we call this as a 25% more than a thickness of slab. What? A drop thickness, okay, and 50% more drop thickness compared to slab thickness, okay. So what happened? 200 mm is the slab thickness. What we done? 200 mm is drop thickness plus 200 mm 25% is 50 mm. So 200 per 50 is equal to 250 mm. Same thing assume 200 mm, okay, is a slab thickness. 50% more means 250 is 100. 250% is 100. So value is 300 mm, right? So the drop thickness is 250 or 300 mm. In between this you can take anything. So what we do? We do 200 mm drop thickness, right? Now we are going for the step 2, column strip and middle strip. Okay, so column strip, we have a size of panel square is 6 by 6. So along long, along short, both are the fixed, okay, oh sorry, same dimension. Along longer direction, column strip dimension is same. Along shorter direction, column strip dimension is same, because we have a square panel, right? That means we have a square panel. So column strip and middle strip both are same. Along short, along long, width are same, okay. So twice into 25 into L1, so 2 into 0.25 into 6000, so 3000 mm. Same thing for the twice into 0.25 L2, 2 into 0.25 into 6000, so 300 mm. It's the size of column strip, okay. So provide width of column strip is 3000 mm in both direction. Why? Because we have square panel, so on along longer, along shorter span, width is not changing. So similarly, width of middle strip is 6000 overall length minus 3000 width, so 3000 mm in the both direction, okay. Now we are going to provide a drop width, provide a width of drop equal to width of column strip in the each direction. So size of drop is 3000 by 3000 by 250 mm, okay. So size of drop is equal to width of column strip, okay. We discussed this in the previous lectures, okay. Drop size is fixed as a column strip. Here is a figure, you can see same is a drop figure, okay. Now we are going to calculate load. Step 3, load calculation. We have a tool, okay. Thickness of slab 200, thickness of drop 250. So first of all, self weight of slab is 3 into 3 into 0.25, 3 by 3 into 0.25, or 6 by 6 minus 3 by 3 into 0.20 into 25 by 36. Why this happened? Why? Self weight of slab is calculated like this. Why? Let's check. Now we are going to calculate a load. So first calculator, we are going to calculate a self weight, okay. Okay, self weight. So self weight equation is thickness into density, okay. So overall I can say density is 25 because we have a concrete here, but thickness is changing. Look at here, it's 200 mm and 250 mm, so thickness is changing. So what we do, I divide this 3 meter by 3 meter slab into 250 thickness, So I calculate 3 into 3 into 250, not 250, 0.25, sorry, 0.25. Then after plus, because we have this panel. Okay, so this panel is converted as 6 into 6 minus 3 into 3 into 0.20, right? But look at here, there is a thickness is multiplied by area. Okay, thickness is multiplied by area. So what we do, 25 divide by 36, 6 by 6 meter. So first we done thickness into area into density, then after again divide by area, right? So this is the equation of self weight, and we found the value is 5.30 kilonewton per meter square, right? Floor finish and partition wall assume 2.70 kilonewton per meter square because there is no given, so we assume it. Third is live load is given, so total load is 12 kilonewton per meter square, dead load 5.30, 1.7, so dead load is here, live load 4 kilonewton per meter square, dead load 8 kilonewton per meter square. Then after we found the factor load, which is 1.5 into 12, so 18 kilonewton per meter square, right? Now we are going to calculate a stiffness, calculate of stiffness alpha C, right? So for column UC so 4 EI by L, 4 EI by L, E is as it is, but I equation pi by 64 into 500 raised to 4. We have a circular column. Right? L is length is 4 meter, 4 meter height. So value is 3.068 into 10 raised to 6 into E. For the slab KS 4 EI by L, 4E into 6000 into 250 cube, 6000 into 12, so 5.208 into 10 raised to 6 E, right? It's the calculation of stiffness. Now we are going to alpha C, Kc by Ks, 2 into 3.068 into 10 raised to 6 E, twice into 5.208 into 10 raised to 6 E. So alpha C is 0.589 calculated. 0.589 is calculated, right? Now we are going to check for the correction due to pattern loading. We have to calculate pattern loading, but ratio, dead load, live load. But for the pattern loading, first of all we have to go IS 456 2000 clause number 31.4.6 page number 56. Let's check. Okay, now here IS 456 2000 page number 56 clause number 31.4.6 effect of pattern loading. So what this line say, clause say, in the direct design method when the ratio of live load to dead load exceed 0.5, then we have to do effect of pattern loading. We have to calculate correction, right? In the previous lecture there is 1% correction in a shorter span, right? But this time if ratio of live load dead load exceed 0.5, then we have to do pattern loading. Live load dead load 4 by 8 is 0.5, so check for the pattern loading is not required because ratio is less than 0.5. Right? So check for pattern loading is not required here. Now we have the fifth step, total design movement. So no correction in this example. So design moment equation MOL, MOS, because longer span, shorter span both are same. So both moment are same. WL2 ln square divided by 8. So W is 80 kN cube. We calculated load earlier. So round column shall be considered as a square column of the same area. Diameter of the column head 1000 mm. Square size of column head. So 880 mm. What we do? We have a round column and round column head. We convert its round column head to the square column head. How? First, we have a diameter of column head 1000. We found the area. We found a area of round column head. Then we do the square root to found the length or dimension of a square size column head. Okay, it's just imaginary thing. Okay, we don't do it in the practical method, but for the calculation purpose, we do a round column head, convert into square column head, and find the diameter. Right? So we found 880 mm diameter of square column head. Right? So L1 is 6000 minus 880, so 5120, so 5.21 meter is the length, is ln of internal panel. So MOL, MOS, moment, 6, L2 is 6 fixed, okay, ln is 5.22, so moment is 353.9 kilonewton into meter. Now we are going to provide a reinforcement along short span. Reinforcement along short span. Okay. So moment is fixed. Column strip 3000, middle strip 3000. Both are same. Both are same. So positive moment, depth is change. Negative moment, depth is change. Negative moment, depth is change. Positive moment, depth is change. Why? Why? Imagine column strip on the column and the positive in the middle. Okay, okay, positive in the middle and negative. No, sorry. Same thing. Okay, right? So at the middle drop we have, so depth will be changed. On the column strip we have a middle portion has drop, so depth will be changed. That's why here is a drop. Okay, so here different depth. All the method are same. 0.65, 0.35, 0.65, 0.35, negative 65, positive 35%. We discussed it earlier. 70% and 60% for the positive, 75% for the positive, 60%. Right? So 353.90, 353.90 is the moment. So here is we have a moment 172.53, 74.32, negative and positive. Same condition. 0.65, 0.35, 35.35 minus. We subtract this value. Right? So 57.50, 49.50 kilonewton into meter, kilonewton into meter. So PT by the equation, you all remember these things. So total AST 2295, 1234, 956, 824 mm square. Then after AST per meter, 765 mm square. So by this AST we provided 12 mm diameter bar at 140 mm center to center. 410 provide 10 mm diameter bar at 180 mm center to center. 318.5. So middle strip we have a 8 mm diameter at 150 mm center to center. 275 mm. We provide 8 mm dia at 180 mm center to center. So our flat slab design is completed. Right? Now we are going for the check. Step 7. Check for the 2 shear. Okay. So for the check for the 2 shear we will do D by 2 critical section. We done it earlier lectures, same things. Okay. from the face of the column head, right? Yeah. Okay. Now d dash 880 plus 1125 1125, so 1105 mm. So Vu is equal to 6 square minus 1.05 whole square into 80. So Vu is equal to 626 kilonewton. It's a shear force. It's a shear force on column. Shear force on the column. So B0 is 4BD square, 4 into 110, 4420 mm. Tau is equal to Vu upon BD. This equation from the IS 456 2000 page number 5859. So value is 0.6. Tau value is 0.629 Newton per mm square. So tau c dash is equal to Kc into tau c. So Ks equation is 0.58820, 1.5 more than 1. So Ks is equal to 1. So tau c is equal to 0.25 under root Fc. So value is 1.11 Newton per mm square. So tau v is less than tau c. It's okay. So no reinforcement is required. No shear reinforcement is required. Here is a sketch. Okay. So we are going to draw this sketch in the Microsoft whiteboard, right, students? So you can see here, this is the sketch of reinforcement. This is a 12 mm diet, 140 mm center on column strip as well as on the middle strip, right? Here is a cross section of a middle strip. Cross section of a middle strip, you can see 6000 mm middle strip. So here is the flash slab design sketch is completed. Drop and with column head. So now we are going to give some practice question. The first is determine the design moment for the interior panel of a flat slab without drop and column head with following data. So in this example, you don't have to design a flat slab. You just have to find design moment, right? Slab 20 by 30 mm, panel size 4 by 6. Imagine there is a slab is 20 by 30, means whole room dimension is 20 by 30 and one panel dimension is 4 by 6. Live load 4 kN square. Floor finish is 1 kN square. Size of column 500 by 500, means a square column. Floor to floor height 4 meter, right? Use M20 concrete and Fe415 grade. This type of example asked in GTU winter 2017. The second example is design an interior panel of a flat slab having equal panel of 6 by 6 meter. The internal columns are 400 mm in diameter and column head is 800 mm in diameter. Story height above and below slab is 4 meter. Design the flat slab with drop and column head. With drop and column head, take a live load 4 kN square and use M20 concrete and Fe415 grade of steel. This type of example asked in GTU summer 2017. So these two are practice questions. Practice it and try to learn. And if you don't understand anything, ask me. I share a link of a Google form, okay, for the question. If any question, you just ask me on the Google form. As soon as possible, I will try to reach you by your email, right? Get up and do something by Barack Obama. Nice tagline.